Let's take a closer look at our series pass voltage regulator, which would be categorized as our linear voltage regulator, and we'll come back to our switching power supplies in later videos. So here below we have a block diagram of our series pass regulator, and in a little bit we're going to take a closer look at a discrete circuit that can be used to represent this. So why is this called a series pass regulator? Well, we notice that there are some devices or some device that is in series between our raw DC input and our output. And so what that means in terms of efficiency is any difference between our input on the left and our output on the right is having to be dissipated or lost in this series pass device. So as we've mentioned previously, our efficiency isn't going to be as good in this type of regulator as it is in our switching power supplies. But this type of regulator can still be useful, particularly for low voltage supplies. So for low voltage supplies, this type of regulator is acceptable. So we say that's good. If we're talking about high voltage or low current power supplies, typically we're going to use something called a shunt regulator, but we're not going to focus on that in this video. So let's just take a look at some of these components before we look at our discrete circuit. So as I've already highlighted there, we have our series pass devices, and we'll see more what that is in a little bit. But the other key components, note we have some type of voltage reference down here. And so as we talked about in the previous video, this is typically going to be a Zener diode operated in the reverse breakdown mode. And what we're using is we're comparing this reference voltage to some feedback voltage coming from our output. So notice we just have a very simple voltage divider with R1 and R2. So we're sending some scaled version of our output V feedback to be compared to this reference voltage in some difference amplifier. So this difference amplifier is then communicating to the series pass device, which is going to adjust in order to keep this load relatively constant. A couple things to note about the general block diagram before we move on to looking at a specific circuit is that we need for this raw DC power source on the left to be large enough to power all of these other blocks. So let me just write that out. So our raw DC needs to always have enough power to power, we'll say, the other blocks. And so by other blocks, clean that up a little bit. So our other blocks, and so of course by our other blocks, that's just these other three components: our voltage reference, our feedback amplifier, and our series pass device. And so what does that mean in terms of any filtering that is required of this raw DC power source before we put it as the input to our regulator? Well, what that means is if we have a, let's say a half-wave rectifier, maybe we have a half-wave rectifier, so we can't just send in a signal where we have this coming up to some maximum and then it's coming back down to zero. So if we have something like this, that would not be good, because once we're down here at these points where we have zero voltage, we're not going to have enough power to power all of these other devices. So often cases we might still need to put some type of capacitor, a relatively small capacitor, so we could clean this up a little bit. So maybe instead of something like we have here, maybe we use that same half-wave rectifier, but we put a small filtering capacitor, so maybe we get something that looks like this. So we could still have a relatively large ripple, so long as it is always a large enough voltage and therefore large enough power to power all of those other blocks. One other thing to keep in mind too is, of course, these amplifier blocks, both our feedback amplifier and our series pass device, are typically going to be transistors. And although it's not something that we're going to explicitly talk about in this class, something very important when we're talking about any type of circuits is the frequency response. And so the behavior of these transistors is going to change based on what the frequency is. And so typically these types of series pass regulators are going to work well into the low kilohertz range, and not so well as the frequencies get higher. But if we recall from our previous equation, if we are filtering with a simple capacitor, we know that our capacitance is equal to IDC divided by our V ripple times F ripple. And so what we just said was that if our frequency is getting higher, then the series pass regulator doesn't work. Well, if that frequency is getting higher, that means our capacitor doesn't have to be such a large capacitor. So if it gets really high, we can switch back to just using a simple capacitor in parallel with the load. But definitely frequency response is something you want to keep in mind as we're talking about this. Okay, so let's look at a simple discrete circuit that sort of represents this block diagram. So this has all of the elements we just saw. We see, for instance, here is our series pass components. Here is our feedback amplifier. Here is our voltage regulator, our Zener diode. So we know it's a Zener diode because we have sort of a little Z as opposed to the flat line across our triangle there. And of course we have our raw DEC input on the left and our output on the right with this voltage divider, so we can get a portion of that and compare it to our raw input voltage. So what I want to do in the rest of this video is do just a qualitative analysis of this circuit, and then we're going to come back in a later video and do a more detailed quantitative analysis. Because what we ultimately want to see from that quantitative analysis is how does our output change as we see changes in our VRAW and as we see changes over here on this load side as well. So first of all, let me take a step back and say this circuit is by no means sort of like the ideal series pass regulator. It's not state of the art or anything like that. It's just a good simple starting point. So typically we'll have IC voltage regulators, and that's going to be sort of the preferred method, and we're going to come back in a later video and we're going to talk about those. So let's just say for now our IC voltage regulators are preferred. And so let me see, I think I've misspelled preferred. Good thing I'm not an English teacher. So our IC voltage regulators are generally preferred, but again, this is sort of a good simple example where we can easily point to what parts of the circuit represent parts of our previous block diagram. Okay, so let's get into our analysis, and I'll kind of have to be scrolling up and down as we write down some points and look at how that changes things in the circuit. Before we get into that analysis, let me label some voltages and currents to sort of aid in our analysis. So let's call this voltage between R1 and R2. Let's call this our voltage VB1. And the reason I'm calling that VB1 is because that is the voltage at the base of our transistor Q1. And of course, we could also explicitly write our polarities like this across R2, but oftentimes in electronics that leads to our circuits becoming unnecessarily complicated, so we'll just write our voltage next to the node. We can also talk about the voltages for our two transistors, our base emitter junctions, because remember these are going to be important because they are helping to determine the relationship between our IB and our IC. So if our VBE is going down, then our IC is going to go down based on our basic BJT IV equation. So let's label this guy up here too. Our Q2 is going to have a voltage VBE2. And we can also notice that if we want to take it even a step further to aid in our analysis, let me call this voltage VE1. So this is the voltage at the emitter terminal of our transistor 1. This is the voltage at the emitter terminal of transistor 2. And we can call this point here the voltage at the base of transistor 2. Okay, so that's sort of all the important voltage, all of our important voltages. Well, no, take that back. I forgot one over here on the left side. So we can call the voltage at this point our voltage VZ. And so that's, of course, our ideal. Ideally, it's going to be a constant voltage, which is serving as our reference voltage. Okay. Let's label a couple additional currents as well. So let's label, and let me use a different color just so it's easier to see. So let's label our base current going into Q1 as IB1. And let's say that has a corresponding collector current over here. That is IC1, collector current in Q1. And we can, of course, also talk about a base current in Q2. And so it might seem like I'm kind of arbitrarily choosing which currents and voltages to label, but we'll see as we go through these steps, these are going to be the useful things to know. And of course, we can always define or label more as needed. Okay, so again, we're just looking at qualitative analysis. So we're not talking hard numbers, we're talking if this thing changes in this direction, what's that doing to our other variables? So let's go sort of step by step here. Let's say something has happened on our load side such that our IL is decreasing. So I'm going to indicate this is sort of step one. So we have our IL is decreasing, which is causing the output to increase. And so maybe we've had some change in a load. So of course, somewhere over here, we're going to have some load that we haven't included. So there's some change in the load. And so maybe we're outputting the same power. So if our IL is going down, that means our V naught is going to be going up. Okay, so what does that mean in terms of the circuit? Well, if our V out is increasing, then that means our VB1 right here is also going to be increasing. So let's say that that means our VB, so 0.2 here, is that our VB1 is increasing. And so that's just because, again, we have a simple voltage divider. If sort of our input voltage to that voltage divider increases, then we would expect the voltage across both the resistors to increase as well. So now if our VB1 is increasing, we'll actually see that the VBE1 will also increase. And so the reason for that is because this VE1 voltage, the emitter voltage of Q1, is essentially fixed at a voltage of VZ. So all of that is connected. The emitter is connected to sort of the top side of our Zener diode there. So that VE1 is ideally fixed at VZ. So let's come down here and write that for our 0.3. So for 0.3, we're saying that IBE1 is increasing. And the reason for that is because our VE1 is essentially fixed at that voltage of our Zener diode. So essentially fixed at VZ. Okay, so now we know from our basic BJT IV equations, if this VBI is increasing, then that also means that our IB is increasing. So if our and so let me see, I've got a typo here. So in this third bullet here, this shouldn't be I, this should be a V. So our VBE1 is increasing. And so if that VBE1 is increasing for 0.4, what we have then is that our IB1 is increasing. And so that just that comes from our basic BJT current voltage equations. And then we know, assuming that this is in forward active mode, we can say, well, if our IB is increasing, our IC is going to be increasing by a factor of beta of that, right? Because IC is equal to beta IB. So if IB is going up, then IC is going up, but we also have this factor of beta. So IC1 also increases, and we have an increase by a factor of beta 1 more than the increase that we saw for IB1. Okay, so what is that going to do? So we've increased this IC1, and what that means is we're going to have an increase in the current drawn, and so I've not labeled this, so let me just label a generic current here. So we have some current going through this resistor R3. And so, of course, you can see from KCL that this current through R3 is feeding both IB2 and IC1. So if our IC1 is increasing, then this current through R3 is also increasing. Okay, so let's say that's our 0.6. So our current in R3 is increasing. And so if we're increasing current in R3, we're assuming that's a fixed value resistor. So from Ohm's law, we can say we're also increasing the voltage, right? So if we have V equals IR, so if I is going up, and for constant R, then our V should also be going up. So we can say voltage across R3 increases as well. Okay, so what does that mean then? Okay, so let's come back up here. We've said that we've increased this voltage across R3. So I've defined voltage across it in this direction. So we're assuming that during this whole process, this V raw isn't really changing too much. We have the same sort of input coming, and we'll deal with that a little bit more in our quantitative analysis later on. Of course, that's sort of a simplification. But assuming that that's not changing too much, and this voltage across R3 is decreasing, we see that means we're going to have a lower voltage at this base of Q2. So let's come down here and note that. So here's our 0.7. And so we note that we're decreasing the voltage at the base of transistor Q2. Okay, so if we assume that this voltage VBE2 is relatively constant, so we're saying that shouldn't change too much if we're operating in the forward active mode, what that means then is if the left side VBE2 has gone down, then sort of the right side, our VE2, is also going to go down. So let's come down here, and this is going to be our 0.8. So we're saying we've also decreased our VE2, and that's assuming that our VBE2, that base emitter junction voltage, is approximately constant. Okay, but let's come up here and let's notice that this VE2 voltage is at the same point as our V0. So note that VE2 equals V out. Well, so let's go back to our first point here and see what started all of this. So at the very start, we said our IL is decreasing, which is causing V0 to increase. And then we sort of step through this chain reaction, and we see the end result is that our V0 is decreasing. And so what that means is that an increase has led to a chain reaction that ultimately led to a decrease in that same variable, is that we had negative feedback. And so as you've seen in controls, and as we're going to get into in a later unit in this class, typically whenever we have negative feedback, that's going to mean more stability. So in terms of our stability of this circuit, we're going to see that means more stability in terms of changes in our load, and more stability in changes in terms of our V raw. In the next video, we're going to come back and we're going to take a quantitative look at this circuit, and then we're going to be able to see in more detail how those changes are occurring as we see changes at our input and output.